Okay, so we've gone over the various methods to make a strong argument for having validity. We talked about content validity. Do we have enough items to really capture the construct of interest? We talked about face validity. Do we actually have items that on the face of it look like they're measuring it? And finally, do we have statistical evidence of validity by doing both predictive validity studies, concurrent validity studies, convergent validity studies, and also looking at divergent validity or discriminant validity? The important thing to recognize, though, is that validity truly is building on reliability. And one of the things we need to recognize is that if we have a test that isn't 100% reliable, and we almost never will, there will always be some error, some variance in the reliability of a test. That when we do these validity studies, there's additional error that we're not capturing based on the fact that our test isn't as reliable as it could be in a perfect world. So again, without strong reliability, a test cannot be valid. But also, when we calculate validity, we basically want to adjust for the fact that we also have reliability information. So attenuation is the weakening of a validity due to poor reliability. In other words, the lower the reliability is of a test, of a measure, also the worse the actual validity will be. Now, we're not going to capture that, though, when we do a validity test. We're simply going to find how related is this measure to some other measure. So, for example, if we're doing a concurrent validity study, how well is our measure of self-report depression related to other measures of self-report depression? And we're going to get an R, a correlation, a value. That's going to be basically our validity coefficient. The problem is we need to adjust that for any unreliability in the test. So, there's a couple of ways we can do this. We basically need to validate the coefficient corrected for unreliability. And there's three ways we can do this. We can adjust for the fact that the test itself, our test, is unreliable. We can adjust for the unreliability of the criterion. In other words, if we know that what we're comparing our test to has some reliability issues, we can adjust. And finally, and ideally in some situations, we're going to want to basically adjust for both. Now, you may ask, why do I have to do this, Dr. Nadler? And that's a common question. Again, remember that what the end result of this whole process of validation is to make an argument that we measure what we think we're measuring, and that once we have that, we're going to use that as a tool to predict something. We're going to use it to predict future college performance. We're going to use it to predict work performance. We're going to use it to predict future outbreaks of psychopathology. And if we're doing that, we're not just wanting information of whether it's reliable or valid. We want as an accurate measure as possible of how much variance are we really predicting in that outcome. So we're mainly going to focus on just basically adjusting for the unreliability of our test. So in these examples, these are equations. It's always fairly simple. We're taking the coefficient of one of our scores at the top of the equation by the square root of the reliability at the bottom of the equation. So the bottom of the equation is usually going to be the reliability of the test. So R sub XX is the reliability of our test. RYY is the reliability of the criterion, the test we're comparing it to. And RXY is the uncorrected validity coefficient that we got from our value. So let's look at that first one, unreliability of the test. So RXY goes to the top of the equation. That's the validity coefficient we got by comparing our test to some other test. That's our correlation, that's our R. And we're going to divide it by the square root of the reliability, again, of our test, RXX. This is going to give us our adjusted validity coefficient. We can also adjust that value for the unreliability of what we're comparing it to, and that's the second equation. The only change here is what goes in the bottom. We still have the reliability of the uncorrected validity coefficient, because that coefficient is the same. That coefficient was the relationship between our test and another. The only thing we're changing in the second equation is instead of the reliability of our test, we're putting in the reliability of the actual test we're comparing to. And the final equation to the far right is actually if we want to adjust for both. This is what we would do if we're really wanting to get at as accurately as possible what the true predictive relationship is between the measures we're looking at. So let me actually walk through the math for you on the next slide. So again, we're just focusing on unreliability of our tests. So we've done a validity study. We've actually looked at the predictive validity or concurrent or convergent, any of those methods we use that gives us an R. But we want to find out what is actually going on once we actually include the unreliability of the test. Now, what this is basically going to show is if the test was 100% reliable, what would the coefficient be? So what we're actually calculating here is how far off are we from perfect. So this is what we're estimating. So in this case, our reliability was 0.55. That's not a very reliable test, by the way. Remember, we kind of made the argument in the reliability slides. We want to see this at 0.7 or higher. We actually still tested our test. We compared it to another test that measures the same construct, and we found the uncorrected validity coefficient, the relationship between our test and another test, was 0.35. So we're just going to plug those numbers in. The top of the equation is our validity coefficient from this study, 0.35. The bottom is the square root of our reliability. So the square root of 0.55 is 0.74. 0.35 divided by 0.74 is 0.47. So notice the amount we calculated is actually a larger R, because again, this is telling us that if our reliability was at 100%, if it was perfect, then our validity coefficient would be 0.47. It wasn't, though. It was unreliable, and therefore it's actually 0.35. So this is kind of a way for us to determine, it's an illustration of how better reliability would result in a stronger ability to predict with our measure. So what we're getting here is we're calculating what the perfect validity coefficient would be if our test was perfectly reliable. That's the final number that we get from this equation. And it also illustrates how unreliability weakens our validity. So if we had perfect reliability, we would have had a relationship of 0.47. But we didn't have perfect. We had kind of poor reliability, 0.55, and that's why we actually got the uncorrected validity coefficient of 0.35. The final thing I want to talk about as far as making an argument validity is yet another tool, and this is factor analysis. A factor is a set of observed characteristics that can be statistically and conceptually related. And factor analysis is a family of methods that classify several items into groups of related factors or latent variables. So basically, a factor is a statistical test for a single construct. A good example of a factor analysis is the Big Five personality model. So basically, conscientiousness, openness to expression, extroversion, neuroticism, and conscientiousness. So that basically makes up the Big Five. How we know there's a Big Five is that previously in personality research, personality was defined by adjectives. So basically you describe people. He's happy. She's shy. He's conscientious. He's nervous. And what researchers did is they took all of those various adjectives, literally hundreds and hundreds of possible ways to describe people's personality, and they had people rate themselves on them. Hundreds and hundreds of people. And then they submitted all that data to a factor analysis. And what the factor analysis kept coming to was a solution of 5 factors. It basically said out of all of these items you're measuring, they clump together into 5 clear constructs, conceptually related, latent, or hidden variables. In other words, there wasn't one elephant being discovered. There was 5 separate animals, each one a major construct, a major 5 factors of personality. So this is done not logically, this is done purely statistically. And it's done by finding similarities amongst the various items. It's most often used in survey research to see if a long series of questions can be grouped into smaller sets or aggregated into smaller numbers. So the Big Five is usually measured with between 50 and 150 items. Well, it would be very hard to conceptualize personality based on someone's score on 150 items, but it's pretty easy to conceptualize it on the aggregate of those items into these 5 big factors. So, for example, what a factor analysis does on a very simple level is we look at the correlations between items. So I've got 4 items here. I keep in the background. I'm interested in people. I have a vivid imagination. I'm full of ideas. And we're just looking at the correlations between those items. So A and B, I keep in the background, and I'm interested in people. Those are related. In fact, technically, we'd probably find that to be a negative relationship. So if you highly endorsed I keep in the background, you're probably less interested in people. But if you don't endorse being in the background, you probably are interested in people. I have a vivid imagination and I'm full of ideas. Again, we see point 8, highly related. So now notice, though, that I keep in the background is not related to I have a vivid imagination. I'm interested in people is not highly related to I'm full of ideas. So you can start to just look visually and see there's some of these items cluster together, A and B and C and D, and other items do not cluster together. Now, this is pretty simple because we only have 4 items. Factor analysis allows us to look at this in a much bigger picture with much larger numbers of items. So we can start actually looking then and thinking about the actual factors or constructs. So A and B, for instance, seems to be getting more at extroversion, while C and D are getting more at openness. Now, both of these are parts of personality. So we're still measuring personality, but we're able to actually, with factor analysis, start to look at the subconstructs that we'd expect to find in personality. So, final slides, validity and test bias. So bias is a factor inherent in any test that systematically prevents accurate impartial measurement. So bias always implies a systematic variance in test scores. Prevention during test development is the best cure for test bias. So bias is when we're capturing an additional construct that we don't want actually in there, but we systematically, reliably measure it. So a common bias in intelligence testing is cultural bias, social economic bias, and sometimes, as a part of cultural bias, ethnicity or racial bias. So you have to be doing this. Once it's in the test to say. You have to often think of, am I asking questions that are capturing additional factors that I don't want actually in there? Another issue with test bias can be rating error. So a judgment resulting from the intentional or unintentional misuse of a scale. So, for example, raters may be too lenient, too severe, or too reluctant to give ratings at the extreme. Central tendency error. So again, rating error, if everyone is rating everyone highly, that's too lenient. And again, you can't make discriminations then because everyone's getting the same score. Or if the raters are all going too severe, giving low ratings to everyone. Again, a problem, as is the middle point, never giving extreme scores in either direction. Another issue with rating error is people do tend to fall prey to halo effect, a tendency to give a particular person a higher rating than he or she objectively deserves because of a favorable overall impression. A good example of this is in our society, there's often the beauty equals good stereotype. Disney films highly support this in our culture, and it's the belief, and it has been found in social psychology research, that the more attractive someone is, we tend to make general broad assumptions that they're also more sociable, that they're more likable, that they have more friends. We don't know that. We don't have objective information on that. We're making a halo effect. So there's a lot of ways that we can get bias into a test, and we do want to be considering, are there ways to reduce this influence? Because any bias is adding error, and it's going to get us farther away in our observations from our true score. So generally speaking, one of the things that we want to look at as a final test of validity is how fair is our test. So once we have evidence of reliability, once we have evidence of validity, we also want to ask how fair is the test, the extent to which a test is used in an impartial, just, and equitable way.